Hello everyone, I'm Dr. Mehraei, and today we are going to talk about chi-square distribution. We already talked about different distributions, including discrete ones like Poisson distribution, binomial distribution, or normal distribution, and t-student distribution as continuous ones. And today we are going to talk about chi-square distribution, which is a continuous distribution as well. Specifically for normal distribution and t-distribution, we know that we use them for estimating the population mean. So we use it as a estimator for population parameters and specifically for finding the mean. But for variance of the population, we need another one. And that's why we introduced chi-square. Pearson was the one who came up with this idea for a specific uh, particular case of gamma distribution that we will also show you why we are saying that. And we just powered uh, all data that we were uh, taken from a normal distribution. We powered all of them by 2, and we derived uh, the chi-square distribution from it. I don't want to go through the detail about the proof of that. This is out of the scope of this course. But anyway, let's go through the application. And I chose one specific application for you, which is very useful, especially when you want to test whether your data follows a specific distribution or not. Okay, so first thing we should know about the probability density function of chi-square. So this is the one, and you can see the parameter as V. V is actually degree of freedom, nothing different than that. So whatever you know about degree of freedom, this is the same thing here. Even for one population case, we have the same formula, like this is n minus 1, sample size minus 1. And that's why I say that chi-square is a particular case of gamma. You just choose degree of freedom over 2 for the first component and half for the second component of gamma, and you will construct a chi-square distribution. For the expectation and variance, you can see how we can calculate them here. So expectation is equal to degree of freedom, and variance is equal to twice bigger than the mean, which is 2 times uh, degree of freedom. And as we change the degree of freedoms, you can see we have different shape for our chi-square distribution. And one thing you should notice is that it starts from 0. We don't have any negative values here because we powered everything by 2. That's why we show such notation for chi-square, x power 2. It shows that we powered already everything by 2. So this one is very similar to variance the way it is, right? And there's a reason that it's happening. Okay, so the whole goal for introducing chi-square was to be able to run some tests using that. And the most important one I could say is goodness of fit test. This one is very useful in order to check whether the observed values, or better to say the data that you collect from somewhere, follows a specific distribution that you expect from it or not, whether your data is normal distributed or not, whether your data follows binomial distributions or not. Or even sometimes you want to check or compare 2 different populations together using chi-square. This is again possible. All right, let's see how we can do that. For this formula, first of all, when we say K, it means that we are trying to put our data into segments so that we will define everything in terms of discrete distribution from the beginning. And I will show you in the example why we do that. Otherwise, this method will be useless. And in other books, they prefer sometimes to use notation like OI and EI instead of writing like this. So it will be I equal to 1 going to N. So what do we mean by that? These are your observed value from your experiment, and these are the values from your the one that you expect from it. So when you run an experiment, you observe something, you record everything, and these are your data. Then you can compare it with the one that you expect. Even you can calculate it before running that experiment. So I will show you in the example, and it will make sense then. So this is the way that you construct, you calculate your test statistic. And as soon as you calculate it, it's easy to find p-value, like before. So whenever you want to calculate p-value, we need the test statistic. But you know, the format is different from the one we introduced you for normal and T-student, right? And for this is a bigger instead of less than, because as you saw in the pictures, everything is accumulated on the right side. We have only positive terms. So we prefer that we show everything on the right side, and in the example you will see better. Let me show you in the table. Like for example, assume that the degree of freedom is 4. It means the sample size was 5 in one population. So 5 minus 1, this is 4. And the test statistic calculated to be exactly 1. So 1 is between these two numbers. And you can see p-value from here. So these are the probabilities, degree of freedom, V or DF, doesn't matter. And as soon as you fix one row as the degree of freedom, then you find where is your test statistic. It is between these two numbers. So you can say your p-value is between 90% to 95%. So you see, it's very easy to find the p-value like this. And since this is one-sided case, we don't need even two-sided, because as you saw on the graph, everything is accumulated on one side anyway. So let's practice it in an example to better understand about goodness of fitness of chi-square. Okay, so assume that we toss a die 90 times, and these are our observations. So when I meant by observation, this is what it is. So for example, for 1 it happened to be 20, for 2 happened to be 15 times, and so on. Now this is the question: is it a fair die? Is it unbiased? If this is the case, then there should be a way that I can test it. And what's my confidence level? This is important. From now on, as soon as we learned about confidence interval and then hypothesis testing, confidence level is very important. So that when I say this is fair or not, I should give a probability after that to say 95% I'm sure that this is the case. So confidence level very important in that scenario. All right, so what's our null hypothesis? We say that this distribution that we have, we don't know which distribution it is. Is it a discrete uniform distribution? What do we mean by that? We already talked about discrete uniform distribution. It means that all the probabilities for each one of these numbers should be exactly the same, which was 1 over n, 1 over your sample size. So it was like, in this case, we have numbers from 1 to 6. If it was, for example, 2 to 7, there was another way to calculate it, not necessarily sample size, then your value. You know what I'm talking about? We had a slide about it. Okay, so 1 over 6 is the probability. But these are numbers, not probabilities. Why is that? Because 90 times we toss that die. So 90 times 1 over 6. This is our expected probability for 1. For 2, this is 1 over 6 multiplying 90. Why this is the same? Because we want to test whether this is a discrete uniform distribution or not. So as you can see, as soon as I say this is null hypothesis, you should write what is alternative hypothesis. So F not equal to discrete uniform distribution. Okay, so degree of freedom, or V, is equal to n minus 1, your sample size minus 1, which is 5. Okay, then your expected value for each segment. This one, we already talked about it, why this is the case. So this is what you expect, even before running the experiment. Now, 90 times you throw that die, and you see these are your observations. So based on the formula, one by one, you can decrease it. Like the first observation, the first segment, when I say segment or category, this is what I mean. The first segment has 20. So 20 minus 15. All the things are the same number, 15 everywhere. And you divide it again by this number because this is exactly what we mentioned inside this formula, you see? So 1 by 1, observed value minus expected one, divided by finally 15. And 1 by 1, you do it, power it by 2, and at the end, you see you should divide it by the same number. So instead of separately, I divide them by 15 for each segment, you can just write it at once because there are summation between them, you see. So after your calculation, you have 5.2 as the result of your test statistic. As soon as you find it, it's easy to find the p-value. So we have the degree of freedom, we have test statistic. Let's take a look on our table. So 5.2, where should I look in this table? First, degree of freedom. Let's fix it. It is 5. So inside this row, where is 5.2? I should look up for it. So I understand this is between these two. So between 20% to 80%, right? So I can mention that this is between 20% to 80%. You may say I want to approximate it, get an average. I'm fine with it. But let's see why we should wait a little. Maybe we don't need even to do that. Okay, so p-value is between 20% to 80%. What is your alpha, your type 1 error? This is 1 minus your confidence level. So 1 minus 95%, which is 5%. So your p-value happened to be more than that. Even the smallest value that p-value has is bigger than your alpha. So you see, that's why I waited to get an approximation for my p-value, because I wanted to check it more accurately. You see, that's why I understood that your p-value, even in the worst scenario, still is bigger than your alpha. So whenever p-value is more than your alpha, what happens? We cannot reject H0. We don't have enough evidence to do that. In which confidence level? 95%. Okay, so whenever you want to reject H0, your p-value should be less than alpha. This is also the same case for t-student and normal distribution that we talked about everywhere. All the tests that you have, p-value should be less than that. Otherwise, there are not enough evidence to reject your null hypothesis. So if you have noticed, since the time we have covered lecture 6, the new topics strongly depend on the previous lectures. So please go through all the lectures carefully and know that it's never too late to learn what a p-value is. I hope it was a useful lecture for you, and don't forget to subscribe to our channel to be notified about our future lectures. See you guys.